Everybody, can you please stand up? Black Mayor, please lead the prayer. Amen. Good morning, class. Good morning. Before you sit down, can you please pick up the pieces of papers under your chairs? Okay. Who is absent for today? None? Very good. You have a perfect attendance. Okay. So, what was our topic last meeting? Anyone from the group? Yes. Okay, very good. Now, we will discuss about the Euler's 5 function or the Euler's totient function. So, but before that, let me read to you the objectives for this topic. So, objectives. At the end of the lesson, the students will be able to, first, know the proponent of the Euler's 5 function and define the meaning of Euler's 5 function. Second, identify the theorems of Euler's function and prove the given theorems. And lastly, appreciate the importance of Euler's 5 function. Okay. I will group you into 3. So, kindly counts off from the back. 1, 2, 3. Okay, for group 1, you will sit here. And for the group 2, you will sit here. For the group 3, at the back. Okay. Now, you will answer this activity. So, direction. In your group, answer the jumbled letters below and present your answer in the class with a yell. So, we have here a jumbled letters and you will answer it in 5 minutes. And for your yell, I will give you 3 minutes for you to practice. So, your time starts now. Minimize your voice. Help your group mates. Are you done? Two minutes left. Okay? Time is up. Group 1, present your answer with your yell. Okay, let's give 5 claps for group 1. For group 2, present your answer. Okay, let's give 5 claps for group 2. For group 3. Okay, present your answer. Okay, let's give 5 claps for group 3. So, let's have to check our activity. So, for number 1, it is a number with no decimal or fractional part from the set of negative and positive numbers including 0. So the answer is integer. For number 2, it is a very important number theoretic function having a deep relationship to prime numbers and the so-called order of integers. So the answer here is phi function. For number 3, we have it is a statement that can be demonstrated to be true or accepted mathematical operations and arguments. So the answer here is theorem. And for number 4, we have a relationship or expression involving one or more variables. We have function. And for number 5, we have a given positive integer n is an integer k such that 0 is less than to k and k is less than or equal to n and the k is a coprime to n. So that is totative. So very good, you got the correct answer. These words are connected to our topic for today's discussion. The proponent of Euler's phi function. We have Leonhard Euler, born on April 15, 1707 in Basel, Switzerland, died on September 18, 1783 in St. Petersburg, Russia. He is a Swiss mathematician and physicist, one of the founders of pure mathematics. He not only made decisive and formative contributions to the subject of geometry, calculus, mechanics, and number theory, but also developed methods for solving problems in observational astronomy and demonstrated useful applications of mathematics in technology and public affairs. So this is Leonhard Euler. Let's proceed. So, the history of Euler's phi function. So, Leonhard Euler introduced the function in 1763. However, he did not at the time choose any specific symbol to denote it. In a 1784 publication, Euler studied the function further, choosing the Greek letter pi to denote it. So, he wrote pi d for the multitude of numbers less than d and which have no common divisor with it. So, this is the start of his phi function. Let's proceed. So, this definition varies from the current definition for the totient function at d equals 1 but is otherwise the same. The now standard notation, capital letter of pi of a, comes from Gauss on 1801 treatise Disquisitionis Arithmeticae. Although Gauss didn't use parentheses around the argument and wrote phi a. Thus, it is often called Euler's phi function or simply the phi function. Okay. In 1879, J.J. Sylvester coined the term totient for this function. So, it is also called or referred to as Euler's totient function. The Euler totient or Euler's totient. Jordan's totient is a generalization of Euler's. So, Jordan studied about the Euler's phi function. So, the cototient of n is defined as n minus phi of n. It counts the number of positive integers less than or equal to n have at least one prime factor in common with n. Okay. So now, we have the Euler's phi function. In number theory, Euler's totient function counts the positive integers up to a given integer n that are relatively prime to n. It is written using the Greek letter phi as the capital letter of phi of n or this symbol which is also a phi of n and may also be called Euler's phi function. In other words, it is the number of integers k in the range 1 which is less than or equal to k and k is less than or equal to n, for which the greatest common divisor or GCD of n and k is equal to 1. The integers k of this form are sometimes referred to as totatives of n. So, from our activity lately, what is totative? Yes. Okay, very good. So, that is totatives of n. I am too fast? Okay. So, actually, this is the history. So, for the definition, Euler's function of pi of n for all positive integers n is defined as phi of n equal to 1 for n is equal to 1 and for n which is greater than to 1. Phi of n equals to the number of integers less than n and co-prime to n. So note, co-prime or relatively prime numbers are those numbers that have only one common factor, namely 1. So, it is only 1. That means a pair of numbers are said to be a co-prime when they have their greatest common factor as 1. So, the GCD or greatest common factor is 1. That is co-prime or relatively prime. For example, so we have find the phi of 5. So solution, here Rn is equal to 5. So Rn is 5. So the numbers less than 5 are 1, 2, 3, and 4. So we will tally here. So the GCD of 1 and 5 is equal to 1. The GCD of 2 and 5 is also equal to 1. The GCD of 3 and 5 is equal to 1. And the GCD of 4 and 5 is equal also to 1. So, since the answer is 1, the co-prime is 1, so it is a yes, it is a co-prime. So, therefore, the phi of 5 is equals to 4 because 1 the pair of the GCD of 1 and 5 is 1. The GCD of 2 and 5 is also 1, and so on. We have 1, 2, 3, 4. So the answer is 4. Another example. You understand? Okay, let's proceed. Find phi of 8. So the solution here, Rn is equal to 8. So the numbers less than 8 are 1, 2, 3, 4, 5, 6, and 7. So, since these numbers less than to 8, so we pair it. We have the GCD of 1 and 8 is equal to 1. So, it is a co-prime since the answer is equal to 1. For the number 2, we have GCD of 2 and 8. The answer is 2. So, it is not a co-prime because when we say co-prime, the answer will be equal to 1. So, since the answer is 2, so no. For the GCD of 3 and 8 equals to 1, so the answer is yes. And for the GCD of 4 and 8, we have equals to 4. So, since the answer is 4 and not 1, it is a no. For the GCD of 5 and 8 equals to 1, so it is co-prime, yes. GCD of 6 and 8, we have equals to 2. So, since the answer is 2 and not 1, the answer is no. It is not a co-prime. And for the GCD of 7 and 8, we have equals 1. And the answer is yes. For this example, we have the numbers that the co-prime is 1. We have 1, 2, 3, and 4. So the answer for the phi of 8, we have 4. So therefore, phi of 8 is equal to 4. Do you understand? Very good. Okay, let's proceed. So, notice that the phi of 1 is equal to 1 because the GCD of 1 and 1 is equal to 1. In the event n which is greater than 1, then the GCD of n and n is equal to n, which is not equal to 1. So that the phi of n can be characterized as the number of integers less than n and relatively prime to it. The function phi is usually called the phi function. Sometimes the indicator or totient after its originator, the functional notation phi of n, however, is credited to Gauss. Okay, let's proceed. So, if n is a prime number, then every integer less than n is relatively prime to it. Whence, phi of n is equal to n minus 1. So, from our previous example, it is correct. Next, on the other hand, if n is greater than 1 is composite, then n has a divisor d such that 1 is less than to d and d is less than to n. It follows that there are at least 2 integers among 1, 2, 3 until n that are not relatively prime to n, namely d and n itself. So, let's proceed. So, as a result, the phi of n is less than or equal to n minus 2. This proves that for n which is greater than 1, the phi of n is equal to n minus 1 if and only if n is prime. So, take note. If and only if the n is prime. So, we have phi of n equals to n minus 1. Next, the first item on the agenda is to derive a formula that will allow us to calculate the value of phi of n directly from the prime power factorization of n. So, we have the theorem 1. If p is a prime and k is greater than 0, then here is the formula. Phi of p raised to k, which is equal to p raised to k minus p raised to k minus 1 equals to p raised to k times 1 minus 1 over p. So, this is the formula for theorem 1. Okay. Proof. Clearly, please take note. Clearly, GCD of n and p raised to k is equal to 1 if and only if p does not divide n. There are p raised to k minus 1 integers between 1 and p raised to k divisible by p, namely p, 2p, 3p, until p raised to k minus 1 times p. So, thus, the set I, 2, until p raised to k contains exactly p raised to k minus p raised to k minus 1 integers that are relatively prime to p raised to k. And so, by the definition of phi function, the phi of p raised to k equals to p raised to k minus p raised to k minus 1. So, just remember this formula. So, we have the example. For an example, we have phi of 9 equals phi of 3 raised to 2 or 3 squared equals to 3 squared minus 3. And if we evaluate this, we have 9. So, since 3 times 3, 3 squared is 3 times 3, not 3 times 2. So we will multiply it. 3 times 3, we have 9. 9 minus 3, we'll copy this. We have 6. So 9 minus 3, we have 6. So the 6 integers less than and relatively prime to 9 being 1, 2, 4, 5, 7, and 8. To give a second illustration, there are 8 integers that are less than 16 and relatively prime to it. They are 1, 3, 5, 9, 5, 7, 9, 11, 13, and 15. Theorem 1 yields the same count. So this is the illustration. 5 of 16, which is equal to 2 raised to 4 equals 2 raised to 4 minus 2 raised to 3 or 3 cubed. So 2 times 2 equals 4 times 2 equals 8 times 2 equals 16 minus 2 times 2, 4 times 2 equals 8. So we have 16 minus 8. So the answer for this number, 16 minus 8, we have 8. Did you get it, class? Okay, very good. Okay, we have another example for theorem number 1. We have 5 of 575. So the solution, we will use the formula. We have 5 of p raised to k is equal to p raised to k minus p raised to k minus 1. So since our n is 575, we have 5 squared times 23. So this is the factor of 575. So we have 5 of 575, which is equal to 5 squared minus 5 times 23 minus 23 raised to 0. So if we evaluate this, we have 5 squared, we have 25 minus 5. The answer is 20. And 23 minus 23 raised to 0. And as we all know that if the exponent of the number is 0, it is equal to 1. So 23 minus 1, so we have 22. So 20 times 22, the answer is 440. So the phi of 575, the answer is 440. Okay, let's proceed. So now we have lemma. We now know how to evaluate the phi function for prime powers, and our aim is to obtain a formula for phi of n based on the factorization of n as a product of primes. Now, the missing link in the chain is obvious. Shows that the phi is a multiplicative function. We pave the way with an easy lemma. So the lemma is, given integers a, b, c, the GCD of a and bc is equal to 1. If and only if the GCD of a and b is equal to 1. And the GCD of a and c is also equal to 1. Okay, let's proceed. So, proof first. So the proof for lemma, we have first, suppose that the GCD of A and BC is equal to 1. And put D equals GCD of A and B. Then, D divides A and D divides B. Whence, D divides A and D divides BC. This implies that the GCD of A and BC is greater than or equal to D, which forces D is equal to 1. Similar reasoning gives rise to the statement of GCD of A and C, which is equal to 1. So, for the other direction, take GCD of A and B, which is equal to 1, and 1 is equal to the GCD of A and C, and assumes that the GCD of A and BC is equal to d sub 1, which d sub 1 is greater than 1. Then, d sub 1 must have a prime divisor p, because d sub 1 divides bc. It follows that p divides bc, in consequence p divides b or p divides c. If p divides b, then by virtue of the fact that p divides a, we have GCD of a and b, which is greater than or equal to p, a contradiction. So, in the same way, the condition p divides c leads to the equally false conclusion that GCD of a and c is greater than or equal to p. Thus, d sub 1 is equal to 1 and the lemma is proven. Do you understand? Okay, I am too fast. Okay, kindly ask questions if you have. Okay, let's proceed to theorem 2. So, if the integer n is greater than 1, has the prime factorization n, which is equal to p sub 1 raised to k sub 1 and p sub 2 raised to k sub 2 until p sub r raised to k sub r. Then, the phi of n is equal to p sub 1 raised to k sub 1 minus p sub 1 raised to k sub 1 minus 1 times the p sub 2 raised to k sub 2 minus p sub 2 raised to k sub 2 until p sub r raised to k sub r minus p sub r raised to k sub r minus 1. So, this is our formula. So, we have n times 1 minus 1 over p sub 1 times 1 minus 1 over p sub 2 until 1 minus 1 over p sub r. So, just remember this formula for theorem 2. So, example for you to understand. So, let us calculate the value of phi of 360. For instance, the prime power decomposition of 360 is 2 cubed times 3 squared times 5. And theorem 2 tells us that the phi of 360 is equal to, so we will use the formula for theorem 2. So 360 times 1 minus 1 over 2 times 1 minus 1 over 3 times 1 minus 1 over 5. So, if we evaluate this, we have 360 times 1 half times 2/3 times 4 over 5. So, which is equal to 96. Do you understand? You can use your calculator. Okay, let's proceed. We have another example. The phi of 108. So, the solution. So, phi of n equals to n times 1 minus 1 over p sub 1 times 1 minus p sub 2 and so on. So, we have, since our n here is 108, so n equals 108 equals, so we have to factor this. We have 2 cubed times 3 cubed. So, the phi of 108 is equal to 108 times 1 minus 1 half times 1 minus 1/3. So, if we evaluate this, we have 108 times 1 half times 1/3. So, equals to 108 times 1/3. So, if we solve this, you can solve in your seat. So, 108 times 1/3, we have 36. So, the answer for phi, so the answer of phi of 108 is 36. Okay, do you understand? Class, do you have any questions? Clarifications? Seems that you understand my discussion, in the same group, you have to answer this activity. So in the same group, you have to get one whole sheet of paper and answer these 3 questions. So in your group, solve the following and show your solution. Answer it quietly. I will give you only 10 minutes. Your time starts now. Answer it quietly. Eyes on your papers. Minimize your voice. Group 3. Are you done? One minute left. Okay, time is up. So, exchange your papers. Your group 1, give your paper to group 3. Group 3, your paper will be on group 2. And group 2, your paper will be on group 1. Okay, let's check. So, for number 1, evaluate phi of 725. So, since our n here is 725, we have to factor it. So, it is equal to 5 squared times 29. So, phi of 725 is equal to, so, we will use the formula. So, we have phi of 725 is equal to 5 squared minus 5 times 29 minus 29 raised to 0. So, 5 squared or 5 times 5 is equal to 25 minus 5. The answer is 20. 29 minus 29 raised to 0. So, the answer is 1. Since if the exponent is 0, the number will be equal to 1. So, 29 minus 1 is 28. So, we have 20 times 28. The answer is 560. So, the phi of 725 is equal to 560. Okay, who got correct? Very good. Let's proceed to number 2. So, find phi of 276. So, our n here is 276, which is equal to, we will factor this 276. We have 2 squared times 3 times 23. So, the phi of 725 is equal to 2 squared minus 2 times 3 minus 3 raised to 0 times 23 minus 23 raised to 0. So, if we evaluate this, we have 2 times 2 equals 4 minus 2. The answer is 2. And 3 minus 3 raised to 0. So, the answer here is 1. 3 minus 1, we have 2. And 23 minus 23 raised to 0. 23 raised to 0 is equal to 1. So, 23 minus 1, the answer is 22. And if we multiply this, 2 times 2 times 22, the answer is 88. So, the phi of 276 is equal to 88. Who got correct answer? Very good. So, let's proceed to number 3. So, solve the phi of 800. So, the phi of 800 is equal to 2 raised to 5 minus 2 raised to 4 times 5 squared minus 5. So, if we evaluate this, 2 raised to 5 minus 2 raised to 4, the answer is 16. And 5 squared minus 5, we have 5 times 5, 25. Minus 5, the answer is 20. So, 16 times 20, it is equals to 320. So, the phi of 800 is equals to 320. Who got the perfect score? Okay, congratulations to Group 1, Group 2, and Group 3. You got the perfect scores. A round of applause. Okay. Seems that you understand this discussion. So, let's have a quiz. So, go back to your proper seats now. Okay? Get 1/2 sheet of paper and answer this quiz. Solve the following and show your solution. 10 points each. So, I will give you, since it is individual, I will give you 15 minutes to answer these 3 questions. 5 minutes each item. Your time starts now. Answer it quietly and eyes on your papers. Abdullah, look at your paper. Okay. 5 minutes left. You can use your calculator to solve. Okay, are you done? Okay. Pass your papers forward. Kindly collect papers. Okay. Do you have any questions? Clarification. Okay. So, you can apply it using the formula. You can solve it for your own. Anyway, I will be giving you my slides. So, if you have no questions at all, for your assignment, research and study about the sum and number of divisors. So, you can take picture or you can copy it in your notebook. So, we will have an oral recitation for our next meeting. So, study. Are you done? So, let's call it a day. Thank you for participating and goodbye. Thank you, students. Goodbye.